Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about the module Ultraviolet Visible Spectroscopy from the paper Thin Films and Technology. So students, let us see what we are going to learn in this module. Firstly, we will discuss about the UV visible spectrometer. Second, the principle of UV visible spectrophotometer will be discussed. Thirdly, the optical band gap measurement, that is how it can be evaluated, will be discussed. Lastly, we will discuss about the UV visible spectrophotometer instrument along with the detailed description of each component. So students, let us start with the basic introduction about the module. Over the years, spectroscopy has evolved as a potential tool for experiments and analysis conducted in research laboratories and industries. This technique is essentially considered by analysts as an apparent solution. The objective should also be to use these spectroscopic techniques in control and industrial laboratories and to develop fully recognized spectroscopic techniques. Spectroscopy involves investigating the interaction of electromagnetic field with the matter. Spectroscopic data. It is represented as an emission spectrum of wavelength or frequency-dependent response. Spectroscopy can be broadly classified into two categories. Number one, techniques based on energy transfer between photon and a sample. Number two, reflections, refraction, diffraction, dispersion or scattering from the sample, altering the amplitude, phase angle, polarization or direction of the propagation of electromagnetic radiation. UV visible spectrophotometer. Ultraviolet visible spectroscopy refers to the absorption spectroscopy in the ultraviolet visible spectral region, wherein the spectrophotometer quantifies the electronic transitions made by the sample. So students, it is an efficient technique to determine the optical properties of any sample, which includes the film thickness, refractive index, band gap, color, and the reflectance properties in general. So here, the optical properties of the prepared of any thin film, they were determined using double beam UV visible spectrophotometer. That is here a model lambda 35 of Perkin-Elmer is shown over a wavelength range of 190 to 1100 nanometer. The spectrophotometer is computer interfaced so that all the parameters like light source, change over position, filter selection, slit width and wavelength can be automatically controlled. Let us now discuss about the principle for UV visible spectroscopy. Ultraviolet UV spectroscopy is an important physical tool which exploits light in ultraviolet, visible, and near infrared range of electromagnetic spectrum. So Beer-Lambert law establishes a linear relationship between the absorbance concentration of absorbers or absorbing species in the solution and the path length. Therefore, UV-vis spectroscopy can be employed for determining the concentration of the absorbing species for a fixed path length. This is a very simple, versatile, fast, accurate, and cost-effective technique. The instrument which is employed for ultraviolet visible or UV-vis spectroscopy is called as UV-vis NIR spectrophotometer. This can be used to analyze the liquids, gases, and solids by using radiative energy corresponding to far and near ultraviolet, UV, visible, vis, and near infrared NIR regions of electromagnetic spectrum. Consequently, predetermined wavelengths in these regions have been defined as UV 300 to 400 nanometer, visible 400 to 765 nanometer, and NIR 765 to 3200 nanometer. So let us now discuss it in more detail. That is, when a light beam is passed through an object and the wavelength of the light reaching the detector is measured. The measured wavelength provides important information about the chemical structure and number of molecules present in the intensity of the measured signal. Thus, both quantitative and qualitative information can be gathered. Information may be obtained as transmittance, absorbance, or reflectance of radiation in 160 to 3500 nanometer wavelength range. The absorption of incident energy promotes the electrons to excited states or the anti-bonding orbitals. So for this transfer to occur, photon energy must match the energy needed by the electron to be promoted to the next higher energy state. So this process forms the basic operating principle of absorption spectroscopy. Potentially, there may be three types of ground state orbitals involved. Number one, sigma bonding molecular orbital, second pi bonding molecular orbital, and third n non-bonding atomic orbital. Besides, the anti-bonding orbitals are sigma star orbital and pi star orbital. So a transition involving the excitation of an electron from s bonding orbital to sigma anti-bonding orbital is called as sigma to sigma star transition. Likewise, pi to pi star represents the excitation of an electron of a lone pair, non-bonding electron pair to an anti-bonding pi orbital. So electronic transitions occurring due to the absorption of UV and visible light are sigma to sigma star, n to sigma star, n to pi star, pi to pi star, as shown in this figure. So the transitions S to sigma star and n to sigma star involves higher energies and thus usually occur in far UV region or weakly in 180 to 240 nanometer region. Thus, saturated groups do not show strong absorption in UV region, so molecules with unsaturated centers undergo n to pi star and pi to pi star transitions. These transitions involves lesser energies and thus occur at longer wavelengths than the transitions to sigma star anti-bonding orbitals. Let us now discuss about how to measure the optical band gap. Optical band gap refers to the minimum photon energy required to transfer the electron from the top of the valence band to the bottom of the conduction band. It is one of the major factors determining the conductivity of a given sample. The band gap of the deposited thin films was calculated from the values of absorption coefficient plotted as a function of wavelength. So students, here alpha is ln 1 by t divided by t, where small t is the thin film thickness and capital T is the transmittance. For a direct band gap material, relationship between absorption coefficient and energy band gap can be expressed as follows, that is alpha h nu equal to constant multiplied by h nu minus Eg to the power half, where h nu is the incident photon energy, Eg is the direct optical band gap of the sample. So, when we plot a graph, which is known as the tau plot, between alpha h nu the whole square and h nu is plotted, and the band gap is estimated by extrapolating the linear part of the tau plot on the energy axis. So this is the photograph of the UV visible spectrophotometer, where all these things, all the components of it are marked. That is, we have the reflectance sample holder assembly, liquid sample holder assembly, thin film holder, and the last one shows a sample mounting carousel. Let us now discuss about the instrument in detail. So the basic components of a spectrometer include a light source, which is UV and visible, monochromator, that is wavelength selector, sample stage, and detector. So a tungsten filament, which is continuous over UV region, is generally used as a light source. So detector is usually a photodiode or a CCD. Photodiodes go with monochromators to filter the light of a particular wavelength to be fed to the detector. While monitoring the absorbance in UV spectrum, the visible lamp must be turned off and vice versa. So the block diagram of the UV visible NIR spectrophotometer is shown in this figure. Let us now discuss each component of spectrophotometer one by one. First, we will discuss about a UV source. The power of radiating the source should not vary in its operating wavelength range. So continuous UV spectrum is produced by electrically exciting the deuterium or hydrogen at low pressures. So the mechanism for the generation of UV light includes creating an excited molecular species that breaks it into two atomic species and a UV photon. The emission wavelengths of both deuterium and hydrogen lamps are in 160 to 375 nanometer range. So the material of the qubits needs to be selected such that it does not absorb the incident light, because this will result in the errors in obtained absorption spectrum. Thus, quartz is usually used. Visible light source. Tungsten filament lamp is used as a visible light source. This lamp can produce light in 350 to 2500 nanometer wavelength range in a tungsten filament lamp. So energy emitted, it is proportional to the fourth power of the operating voltage. Thus, in order to get a stable emission, a highly stable voltage must be applied to the lamp. The stability of the voltage is ensured by using electronic voltage regulators or constant voltage transformers. Tungsten halogen lamps includes small quantities of iodine embedded within a quartz envelope, which also contains the tungsten filament. So the iodine, it reacts with the gaseous tungsten formed by sublimation and produces a volatile compound Wi2. So as Wi2 molecules hits the filament, they decompose and redeposit the tungsten back on the filament. The tungsten halogen lamps usually have lifetime twice to the conventional tungsten filament lamp. Tungsten halogen lamps, they are used in modern spectrophotometers owing to their high efficiency, and their output extends to UV region as well. Qubits. Monochromator source is used before reaching the sample. So light, it is divided in two parts of similar intensity with a half mirror splitter. So one part or sample beam travels via the qubit, having the solution of the material to be examined in transparent solvent. Second beam or reference beam travels via similar qubit, having only the solvent. So reference and sample solution containers have to be transparent towards passing beam. Let us now discuss about the detectors. Detectors detects the intensity of light transmitted by qubits and sends this data to a meter to record and display the values. So electronic detectors calculates and compares the intensities of light beams. Several UV-vis spectrophotometers, they have two detectors, a phototube and a photomultiplier tube, and reference and sample beams are monitored simultaneously. The photomultiplier tube is extensively used detector in UV-vis instruments. It includes a photoemissive cathode. Electrons are emitted from the cathode when photons strike it. Several dianodes. A dianode emits multiple electrons when one electron strikes it, and an anode. So the incident photon, after entering the tube, strikes the cathode. The cathode then emits multiple electrons, which are then accelerated towards the first dianode, whose potential is 90 volts, more positive than cathode. The electrons strike the first dianode, leading to the emission of several electrons for each incident electron. These electrons are then accelerated towards the second dianode to produce more electrons, which are accelerated towards dianode 3 and so on. So all the electrons, they are eventually collected at the anode. So by this time, each original photon has produced 10 to the power 6 to 10 to the power 7 electrons. The resulting current is amplified and measured. So photomultipliers, they are highly sensitive towards UV and visible radiations and have fast response times. However, photomultipliers are used only at low power radiation, as high power light may damage them. The linear photodiode array is an example of a multi-channel photon detector. These detectors can simultaneously measure all the elements of a beam of dispersed radiation. A linear photodiode array consists of several small silicon photodiodes created on a single silicon chip. So the number of photodiodes, they can vary from 64 to 4096 sensor elements on a chip. However, 1024 photodiode is the most common. For each diode, there is also a storage capacitor and a switch. The individual diode capacitor circuits can be sequentially scanned. Charge coupled devices, CCDs. They are like diode array detectors, but instead of diodes, they consist of an array of photocapacitors. Reference beam intensity should suffer little or no absorption and termed as I naught, whereas that of sample beam is called as I. So spectrophotometer automatically examines all wavelength components in a short time. This technique is good to evaluate the concentration as well as molecular structure or structural changes. It may also be used to examine the vibrational and conformational energy levels alterations before and after an interaction with a substrate or a molecule. So students, let us summarize what we have learnt in this module. Firstly, we discussed about the UV visible spectrometer. Secondly, the principle of UV visible spectrophotometer was discussed. Thirdly, that how to measure the optical band gap was discussed in detail. Lastly, the UV visible spectrophotometer instrument details were discussed with the detailed description of each component. Thank you.